a Cauchy-Euler differential equation that is non-homogeneous. So we have this non-zero term sitting on the right-hand side. And so as we've seen in the past, the first step is to solve the homogeneous part. So I ignore this. I pretend like it's equal to 0. I write down the characteristic equation, which is this, right? And I'm getting that from the second derivative is m minus 1, and then the minus 3, m for the first derivative, and then just a constant of 3. Combine everything, factor, you get m is 3, m is 1, and so your complementary solution is c1x cubed, c2x, and of course your fundamental set of solutions is x cubed x. And when you're working these out, it's really tempting to just jump immediately into the homogeneous case, or the non-homogeneous case, and compute the Wronskian and W1 and W2. But to do that, there is a key step which you don't want to forget. And that key step is we need to put our differential equation in standard form. And to do that, I just want the leading coefficient right here to be a 1. So I'm actually going to divide the whole equation by x squared. And the only thing that's going to change in my problem is it's actually going to change what I'm working with on the right-hand side. So when I divide by x squared, I get y double prime minus 3 over x y prime plus 3 over x squared y equals 2x squared e to the x. And now that it's in standard form, now I can focus on computing the Wronskian and everything else. And so the Wronskian actually doesn't change. It's the same either way. The Wronskian here, I'm going to write down my two solutions, x cubed and x, 3x squared and 1, and I'm going to get out minus 2x cubed, just like we did. It's the W1 and the W2. So I actually don't write the original function down. I write the modified function coming from the version of my differential equation where there's a leading coefficient of 1 right here. And when I do that, I'm going to write 2x squared e to the x on this side, x and 1 on that side. And I'm going to get, in this case, what? Minus 2x cubed e to the x. So that's W1. W2, I'm going to get x cubed, 3x squared, and then a 0, 2x squared e to the x, which is going to be, what, 2x to the 5th e to the x. So now that I've got W1 and W2, I'm going to run out of room on my paper here if I'm not careful. I can go ahead and find U1 and U2. And so let's just, we'll slide everything over and we'll squeeze them in here. So U1 prime is just, well, it's W1 divided by W. Well, that works out really nice. It's just e to the x. And so U1 is also just e to the x. That's very good. U2 prime is going to be W2 over W, which is going to give me, what, negative x squared e to the x. And so we learned in class, you can just do by parts twice, but we learned in class you can also write U2 as negative, and then it's going to be, actually it's negative e to the x, and then it's going to be x squared minus 2x plus 2 when you factor everything out there. So that's U2. And so now you can finally write down your solution. So y is the complementary solution, c1x cubed plus c2x. And then I've got my u1 times y1, so that's going to be what, x cubed e to the x. And then I'm going to have plus u2 y2, and so that's going to give me y2 was x. So I'm going to have minus x e to the x, x squared minus 2x plus 2. Notice there are some like terms we can combine here, and so when we do that, we're going to end up with c1. Here, let's actually squeeze this in down below. We're going to end up with y equals c1 x cubed plus c2x plus, and if you factor out, you're going to get 2x e to the x, and you're going to be left with, let's see here, a x minus 1. And so that's it. That is the solution to this differential equation, and we're good to go. So moral of the story is, don't forget to put your differential equation in standard form before you hunt for the particular solutions. Otherwise, you might end up doing a lot of unnecessarily difficult integration. Ciao for now.